Good evening, all. Am I audible?
Yes, ma'am.
Yes, ma'am.
Yeah, and I have shared my screen. Kindly acknowledge if my screen is visible.
Yes, ma'am.
Yes, ma'am. It's visible.
All right, people.
Say,
We'll be discussing this activity questions. And if you have any doubts in this week, we can discuss that, people. Okay. So I think in the previous session that 11.1, 2, 3, and 5 are completed, right? You all remember that, people?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
All right. Or people, do you want to give a look a glance at it? All right. So the 11th week is completely of DFS, right? And recursion. So what is DFS, people?
Depth first search in which we start from a vertex and go in depth towards the from the source vertex to the end vertex, and then we can backtrack, and we therefore form a stack of such vertices.
Yes. So generally, if it is of depth first search, we are just starting and we are just keep going till the end. And if there is no path, we'll keep backtracking and we'll reach the upwards. Okay, and then we'll try to reach the previous step. Its immediate step is taken, and from there we'll try to find the path. Okay, so what is recursion?
When a function calls itself,
Yes, a function that calls itself is said to be a recursion. So what is backtracking then?
so it's the same procedure, but like going back the same form, like as you do in factorial. So you call the function and then recall it over again.
Mm-mm. Okay. So backtracking in the sense of, let's say I'm using one path and I'm trying to move in that way. Okay, if the path is not, let's say here there is no path. So what I'll try to do, I'll backtrack to this space and I'll try to check for the other possibilities. If this is not possible, I'll come to this step. And from here, I'll check is there any other path is available or not. If none of the path available, this is the starting point, right? From there, is there any other path is available to the destination or not? We'll check this. So this is what is said to be a backtracking. So we have to like it's nothing but we are trying to explore the possible ways. Nothing but let's say if I'm going through this way, is it possible to reach a destination? No. So I'll try to move to the previous step. From there, I'll try to find. If that is also not possible, again I'll try to find. Okay. So this is how we'll use the backtracking. Okay, recursion in the sense of the example is like factorial. So factorial, do you all know what is factorial, people?
Yes, ma'am.
Yes, people, what is factorial, ma'am?
The number of ways you can arrange things.
Yes, factorial in the sense of, let's say, from n to 1, all the values, like n into n minus 1 into n minus 2 up to 1. We have to multiply all the values. So this is what is said to be the factorial. So let's say if I have to find the factorial of 5. So how to write it in a recursion, people?
Ma'am, like 5 into 2. Then
Okay, so we'll start with a base case and we define factorial of 0 to be 1 first.
Factorial
So
1, factorial 2, factorial 3, factorial 4, factorial 5.
ma'am, you start
Yes,
with
so
5.
we have to use a base case, right? So what is the base condition?
that's 0
Has to be
factorial to
1.
be 1.
Yes, if the n is equal to 0,
Return 1.
what is 0 factorial?
It's 1.
1.
Which is nothing but 1. How about 1 factorial?
Also 1.
Which is also 1. So I can just give it as if n is equal to 0 or if the n is equal to 1, we have to stop. That is, we have to return as 1. Otherwise,
And you can, otherwise, you will do n times factorial of n minus 1.
yes. Otherwise, that is the else part. We'll just give it as return n into whatever is the function name we have given. N into function of n minus 1. So this is how we'll just write the factorial. Is that clear to you all?
Yes, ma'am.
Yes, ma'am.
Yes, people?
Yes, ma'am.
Great. So in case of DFS, we are going to use this backtracking. So for backtracking, we have to use this recursion. Is it clear?
Yes, ma'am.
Okay. So here what will we try to do is we'll just try to make only 2 vertices. One is of visited. Let's say if I have a value, let's say we have a like position here like A. And similarly, let's say I'm giving one more as B here. And let's say it is C. Let me give here as D, E, something like this. Okay, if I'm starting from A is visited. So from A, I have to visit the other unvisited vertices. So here only of two things. One is of visited and the other is not visited. That is unvisited. Is it clear, people?
Yes, ma'am.
Yes, ma'am.
Alright. So here A is visited. The remaining everything is an unvisited one. So then and let's say I'm moving to this B. So from B, I have to visit the other unvisited vertices. So here A is visited, B is visited. So from B, is there any other vertex which is connected, but it is unvisited? Is it something like that, people?
Mm.
No, ma'am.
Okay, so there is nothing like that. So it will backtrack and it will move to the previous step itself. That is to A. So from A, it will check, is there any other unvisited nodes?
Yes.
So it has to move to, there are C, D, and E. Let's say I'm moving to D, C. So from C, it will check for unvisited. Yeah, it is. It will move to D. Then from D, it will move to E. And from E, is there any other unvisited vertices?
No.
No.
No, it will traverse back to D. And let's say from D, we have one more vertex is something like F. Okay, then it will check from F. Is there any other unvisited node? If not, it will traverse back to D again and then it will check. So from D, is there any other, from D, is there any other unvisited vertices? No. So it will traverse back to the C. So from C, there is nothing, then it will move to E. So this is how the backtracking works. Is it clear, people?
Yes.
Yes, ma'am.
Yeah. I hope now you got a better idea, right? You all able to recollect what we have discussed so far? Okay. So next is if the neighbor of, have you watched these lectures, people?
Yes, ma'am.
Great. So in this lecture, you could see that they would have taken the um place and the timing. So from that timing, let's say day and timing is taken. So from the station they are starting, what are the possible trains and what are the possible stations they can move to the, like they can go ahead with the next stations. Yeah, you can see here, right? So initially they are taking some station, that is ES, and they are taking what station it is and what day it is and then the timing. So if the train reaches at 125 at one station, so from there there has to be a next train which starts after 130, right? That is 125. After 125, what are the trains are there? So based on that, the person could take up the other train. Is that clear?
Yes, ma'am.
Okay, so that is how we'll just try to take all the values in this. Okay. So here they have mentioned this. The neighbors of the stations are trains and vice versa in the DFS tree drawn in the lecture. Is that true or false?
True, ma'am.
Okay, how it is true?
Because from one station you can take the next train.
Okay. So actually the neighbor stations, we can just take the vice versa. Like even in this lecture, you can see that they would have mentioned the station and then next is the train. So E is ET, something like that. Is that clear, people?
Yes, ma'am.
Okay. So the neighbor of the stations are trains and the neighbor of the trains are stations. And next is a mutual recursion is a form of recursion in which two objects are defined in terms of each other. Is that true or false? Yes. So what is mutual recursion first? All right. So mutual recursion in the sense of, so let's say there are two or more functions are there. Each is dependent on the other. That is, if one function is called, based on that, I have to check for the other function call. So I think you might have seen this, right? If it is odd, do this process. If it is even, do this process. So it's like what number we are getting, based on that, the particular function has to be called. Okay. So that comes under this mutual recursion. So mutual recursion is a form of a recursion in which two objects are defined in terms of each other. So the answer will be like true. Is that clear, people?
Yes, ma'am.
Great. So here is the next question, people. Assume that there are 11 nodes in the longest path of a DFS tree drawn according to the concept used in the lecture. So the end of the longest path will be what? Yes, people.
Service station.
You can just check that lecture as well, ma. Yes, people.
Ma'am, I think it depends on the starting node.
Yeah, what is the answer? Yes, people. So actually how this works, so based on what starting point you are taking, right? Let's say the starting point is a station. Based on that, we'll get the value, right?
Yes, ma'am.
Yeah. So here the answer is depending upon the starting node which you are taking. So how many nodes, train nodes can be visited while traversing to the longest path if the starting point is a station? So imagine that we have already discussed that if there is a station, its neighbor is going to be a train. So if there is a train, station in the sense train. So something like this, right? So if it is of something like 11, so the length of the whole path is 11. So how many train nodes would be visited?
10.
5.
Yes, how many will be people?
5. No, I think it's 5.
Okay. Others?
Five, man.
Yes. How it is 5 people?
Because between two stations, there's one train, and we need to count the number of trains.
Yes. So the answer will be 5. Is this thing clear, people?
Yes, ma'am.
All right, people. So now going ahead with the next activity. That is activity 11.6. Okay. So here, so choose the correct statement about the depth first search algorithm. They have given the option. So please tell me which are all the options are right.
Ma'am, the first one, then the third one, then the fourth one, and the last.
People, your voice is too low. Could you please speak a bit louder?
Sorry, ma'am. I said the first one, then the third one, the fourth one,
So
and the
start
last.
from the node I, visit the neighbor node, fine. Then,
The third option, ma'am.
okay, suspend the exploration of node I and explore node J instead. Okay, fine. Then,
Then the fourth one,
mm, keep track of the visited vertices in the dictionary. Great. Then,
the last one.
recursively update the visited each time we explore a unvisited neighbor. Others, is it right?
Ma'am, even
Yes.
second also, explore all neighbors of nodes of I before exploring neighbors. Yeah.
That is
Saying that
BFS.
explore all neighbors of I. It's depth first search, right?
Yeah.
Okay, what is depth first search?
It explores the neighbor nodes and then keep getting in to the next level, and unless it find the path for itself, and when it exhausted the path, then it started going back.
Yes. So let's say if I'm taking the I, so from I, will it explore all its possibilities? Or from I, let's say it is going to J, and then it will go to further path of a J, or will it go back to I and it will it check?
Yeah. So it
which
will
is
go into the depth first, and then it will backtrack to the other options. So second is not applicable. Clear now. Thank you.
actually from I, it will just go to this J, and from J,
J, it will go to the next one.
yes, it will go further to the J's other path, right? It will not go to the before one, right? So
Yes.
once all the paths in J is explored, then it will go to the I,
Clear.
which means here it is mentioned as explore all the neighbors of node I before exploring neighbor J.
Yeah.
But that
That's
is
not
not case, right?
that's not the case. Yes, clear.
Okay, so that's why the third option is right, because we have to stop the parts of I, we have to complete J, and then we have to go ahead with the I. Okay. Is that clear, people?
Clear now.
Yes.
Great. So the next is, this is the tree given, that is A is connected with B and C, and B with EF, E with L and J. And before that, what is breadth first search, people?
Ma'am, when you search a graph level by level,
It looks for the minimum edges to visit all the nodes.
So let's say from I, it will just visit all its neighbors first. Let's say, let me give it a name here. Okay, all its neighbors are visited, and then it will just go ahead with the J, and from J, it will visit all the vertices, and then it will go to K, all the vertices are visited, and then L, and then M, something like this. Is it clear, people?
yes, ma'am.
Alright, so this is how it works. So that is where this breadth first is. So first I have to traverse this whole level, and then the next level, and then the next level. So it's like level 1, level 2, and level 3 elements. In case of breadth first search, we'll just go to level 1, and from level 1, I'll just go to level 2, and level 2 to level 3, and then it will traverse back to the level 2, and then it will just go ahead and it will proceed. Is that clear?
Yes, ma'am, clear.
Great. Okay, so here it is given as starting from the node A, which algorithm will visit the least number of nodes before visiting the D. Let's say if I have to visit this D, there should be a least number of nodes visited. So for which is used, either BFS or DFS.
DFS.
For this DFS, how would it work?
It will go A to C, C to D.
But B is the lower element, right? Comparing to C.
Ma'am, I think it's breakfast search for the second one.
Repeat.
I think it's a breakfast
Okay.
BFS, ma'am.
Okay. All right. So if it is of BFS, how it would have worked?
Ma'am, so you start at A and you explore the nodes of A, which are B and C.
Okay.
Then um, you explore the D node from C because we're going alphabetically.
Yes.
Then E and F.
Okay, so this one we are following the BFS, right? All right. So the answer will be like BFS. And yeah, here is the next question. So starting from the node A, which algorithm will visit the least number of nodes before visiting E? E has to be visited. So for which either BFS or DFS is used? Yes.
Ma'am, DFS,
How it is DFS?
because you start with E, right? It says E. Oh no, no, for three, okay. So you start with the node A,
Yes.
then you go to B,
Yes.
then E, because just you're going deeper and deeper.
Yes. We have to go to the next levels until we reach the end. Sorry, here how it will traverse people in case of BFS. In case of BFS, it will travel from A to B, B to C, C to D, and then E and F are traversed. Then this level is over. Then it has to go ahead with the next level. That is the other next level elements are traversed, and then K and M are traversed. How about DFS? A to B, and then B to
E.
yes, B to
E.
okay. So after E,
Into L.
which alphabet comes first, L or J?
AJ.
J. J.
J, and then
K.
and then
M.
and then it travels to L. After that, it travels to this B. So from B, it is traversing to F. So from F, it travels to G. Then that's it. This whole side is over. Then C, D, and then
H. M.
H and I. Okay, fine. So now, which takes the lesser element to visit the D? Sorry, visit the E. BFS or DFS?
DFS.
Yes. So what will be the answer for this third question then? It's depth first search. Okay. So starting from the node A, in what order will the nodes be visited using the depth first algorithm to reach the node F? So which is the answer here? Yes.
C. Option number 3.
Yes. It's option C because here you can see that, right? Like we have taken the path like A, B, E, J, K, M, L. After that only we are reaching to the F. Is that clear, people? Yes. Okay, so here is the next question. So starting from the node A, in what order will the nodes be visited using the breadth first search algorithm to reach the node F in case of BFS? So what is the order?
Last one. D.
Yes, because here you can see, right? A, B, C, D, E, F. Okay. Is this clear, people?
Yes, ma'am.
Okay. Do you have any doubt in this week 11 questions, people?
Yes, ma'am. Hello.
Yes. What's your doubt?
Activity 11.4 last one, ma'am.
Activity 11.4, right?
Yeah. Uh, uh, 4 number question from which graph this question given, ma'am?
Are you talking about this fourth question?
Yeah, ma'am.
Okay. So let's say, what is the number of nodes are there? 11 nodes, right?
Oh, yeah.
Okay. So first it is starting with the station because they have given the starting point as a station. So what
Oh,
is the station's neighbor one? Neighbor is going to be train. Then train's neighbor has to be station. Station's next has to be train. Again station, then train, again station. Okay. So this is how it works, right?
yes, ma'am. I understood. I think that this question given is according to lecture.
Okay. Okay. So here there are of 11. So here we have the trains in the order like 1, 2, 3, 4, and 5 stations. 5 trains are here. Okay. Yes.
Yes, ma'am.
Others, any doubt, ma'am?
Number 4.
Of which question? Of the same activity 11.4?
Yeah.
What is the doubt in that, ma'am?
The total number of friends.
Yes, what's your doubt in that?
The total number of trains, the count of the trains, right?
Yes, train nodes. So yeah, this is how. So they have said that the starting node is of a station. So that's how we are just giving the starting node as station. So as mentioned earlier, whatever is the starting node, it's next has to be the train. Like, which means like if it is a station, its next has to be train. Train's neighbor has to be station, something like this.
Okay.
Any doubt further? Okay. Any other doubt in week 11, people? Yes, people. Do you have any doubt?
No, ma'am, not at this point of time.
If you have no doubt, shall we wind up the session then, people? All right, people. If you have no doubts, we can wind up the session. Thank you, everyone.
Thank you, ma'am.
People, I'll be here. So if you have any doubts, you can ask now.